Look at the universe today, and you'll find sprawling galaxies, billions of rocky planets, and complex biological life. Now, wind the clock back 13.7 billion years and erase all of it. Before that exact moment, neither space, time, nor matter existed. The entire cosmos started as a microscopic singularity, an intensely hot, infinitely dense point only a few millimeters wide, operating like a supercharged black hole. The Big Bang represents the rapid, violent expansion of the fabric of space and time. It was the instantaneous growth of the cosmos itself, creating the dimensions we live in today. The physical laws that govern us today were not forged in a single instant flash. The modern universe was constructed step by step, driven entirely by a relentless system-wide drop in temperature. As the heat dissipated, it created the specific conditions necessary for each subsequent stage of the universe's development. This graph tracks the temperature during the universe's earliest stage, the radiation era. In its first tens of thousands of years, the cosmos was entirely composed of blinding energy. It was completely void of matter, governed instead by a single, all-encompassing superforce. A period of violent inflation then stretched the universe at incomprehensible speeds. In a fraction of a second, the entire cosmos expanded from the size of a single atom to the size of a grapefruit. That instant surge outward forced a sudden chill. As the temperature plummeted, the unified superforce fractured, and gravity splintered off to operate independently. The cooling continued to cascade. The strong nuclear force broke away next, followed by the electromagnetic and weak forces. The initial superforce shattered entirely into distinct, permanent physical rules. This separation allowed the four forces to take on their distinct, specialized roles. Without gravity acting independently to pull mass together, or the nuclear forces holding the centers of atoms in place, the universe would have remained a featureless void of energy. Even with gravity and electromagnetism successfully separated, the early universe was still a dense, chaotic soup. Loose electrons and quarks churned at incredible speeds, retaining far too much thermal energy to slow down and connect. Over time, the continuous expansion cooled the environment enough for those tiny quarks to lose their momentum. They finally bound together, freezing into the universe's first stable protons and neutrons. As the cooling dial ticked down again, those protons and neutrons successfully fused into solid atomic nuclei. This fusion process created the very first chemical element, helium. By the end of the radiation era, the universe had successfully manufactured its heavy raw materials. But it remained a glowing fog of incomplete atoms, waiting for one more critical drop in temperature to clear the air. That drop arrived during the Atomic Epoch, crossing a vital temperature threshold that kicked off the matter era, a cosmic phase spanning billions of years to the present day. This animation illustrates the exact mechanism of that cooling milestone, called recombination. The erratic, fast-moving electrons finally lost enough heat to be captured by the waiting nuclei. They slowed down and magnetically snapped into permanent orbit. That simple magnetic capture assembled the second element in the universe, hydrogen. Trillions of these newly formed hydrogen and helium atoms drifted outward, transforming the cosmos from a loose scattering of particles into massive, sprawling atomic clouds. Locking the electrons into tight atomic orbits cleared out the dense radiation choking the early cosmos. With the fog lifted, matter secured its position as the dominant architectural force in the universe. Inside those sprawling, massive atomic clouds, tiny imperfections in density allowed gravity to pull pockets of gas together. As the mass accumulated and compressed inward, the seedlings of the first galaxies finally took shape. Deep within those nascent galaxies, the incoming gas generated immense gravitational pressure, eventually igniting the universe's very first stars. These stars introduced a massive thermodynamic paradox. While the surrounding universe continued to freeze, the core of a star acts as a violently hot pressure cooker. That localized heat crushed primordial hydrogen and helium together, acting as a forge that manufactured nearly every heavier element on the periodic table. When those early stars exhausted their fuel and collapsed, they ejected those heavy elements back out into the void. Carbon, iron, oxygen, they drifted out to form the solid crusts of planets, and ultimately, the biology of living organisms. Every single galaxy, planet, and ecosystem we see around us today is the direct result of a precise thermodynamic sequence. It is an unbroken chain reaction of expansion and cooling that built everything in existence.